You'll often encounter the word subtend in circle geometry, so it's important you understand it. It means to be opposite to and to mark the boundaries of. On this triangle, for example, each of its sides subtends the opposite angle. BC subtends angle A, AC subtends angle B, and AB subtends angle C. Subtended angles are also found in circles. On this bicycle wheel, the arc on the circle between the spokes is opposite to the angle at the center of the wheel, and also marks the boundaries of the angle made by the spoke. This angle is therefore subtended by the arc opposite it. Notice that the smaller the arc, the smaller the angle will be. Here, if line segments are drawn from the endpoints of chord AB to O at the center of the circle, then chord AB subtends an angle at O. The arc AB subtends the same angle at the center because it shares the same endpoints as the chord AB. If two chords are congruent, which means they have the same length, then their arcs will also be congruent. Equal chords, or arcs, subtend equal angles at the center. This theorem states that two chords of equal length anywhere on a circle will subtend equal angles at the center. Here's the proof to show the theorem is true for any two chords. We start with equal chords A, B, and CD on a circle with center O. The line segments OA, OB, OC, and OD are all equal because they are the radii of the circle. Also, we know that line segment AB is equal to line segment CD. This fact is given. Therefore, triangle OAB is congruent to triangle OCD, with the reason that all three sides are equal. And this means that angle AOB is equal to angle COD. In this diagram, chord AB subtends angle C on the circumference because line segments join the endpoints A and B to point C on the circumference. Keep in mind that the arc AB, which shares the same endpoints as chord AB, also subtend the angle. The same chord AB can subtend angles at an infinite number of points on the circumference. We can only say that an angle is subtended by a chord if the endpoints of the chord are joined at the vertex of the angle. Here, the angles subtended by AB are in both the major and minor segment of the circle. Angles x1, x2, and x3 subtended by AB are in the major segment, whilst angles y1, y2, and y3 subtended by AB are in the minor segment. Take a closer look at x1, x2, and x3. These angles, which are subtended by the same chord in the same segment, appear to be equal. We will prove this next. Angles y1, y2, and y3 also appear to be equal. Notice, however, that the y angles are obtuse angles, or more than 90 degrees, whereas the x angles are acute angles, or less than 90 degrees. So the chord only subtends equal angles if the angles are in the same segment. Here's another theorem. The angle subtended by an arc at the center of a circle is always double the size of the angle that it subtends at the circumference. To prove this, we'll start by looking at three different situations. In each of these, arc AB subtends angle AOB at the center and angle C at the circumference. In the first diagram, arc AB is the minor arc. In the second, arc AB is the major arc, and we are interested in the reflex angle AOB. The third diagram is an interesting case. Arc AB is a semicircular arc formed by the diameter AB. Here's the proof. OA is equal to OB and to OC in all the diagrams because they are the radii of the circle. Triangle AOC is isosceles and has two equal sides because the sides are formed by radii, and so angle A equals angle C1. Similarly, we know that angle B equals angle C2. Now let's look at angle O1. It is an exterior angle to triangle AOC, so it is equal to the sum of the opposite two interior angles, A and C1. But we know that A equals C1, so angle O1 is equal to 2 times C1. In the same way, angle O2 is equal to angle C2 plus angle B. So angle O2 equals 2 times angle C2. Now we have angle O1 plus angle O2 equals 2 times angle C1 plus 2 times angle C2. This gives us angle AOB is equal to twice angle C. We have proved that the angle subtended by an arc at the center is double the angle at the circumference. Let's talk about our special case, where the subtending arc is a semicircle. Here, the angle AOB is a straight angle because it is the diameter of the circle and has an angle of 180 degrees. The angle at the circumference, which is subtended by AOB, is a right angle. This is an important fact that we can use when we solve geometry problems. When we give this fact as a reason in a proof, we simply write angle in a semicircle. Now for the next theorem. Angles in the same segment of a circle are equal. Remember, a chord divides the circle into a major segment and a minor segment. The angles have to be on the same side of the chord to be equal. We'll prove that angle A is equal to angle B. They are both subtended by arc DC. Arc DC subtends angle COD at the center. We'll call this angle 2x. We know that B equals x because, as we've just proved, the angle at the center is double the angle at the circumference. But angle A is also equal to x and half the size of angle COD because it is also subtended by arc DC. Therefore, angle A is equal to angle B. We give the reason angles in the same segment when we use this as a reason in a proof or when solving a problem. This theorem is used as the basis for navigating a ship safely around a rocky shoreline. A sailor knows the position of 2 points on the shore, as well as the angle that must be subtended by these 2 points to keep a safe course around a dangerous area. Let's work through an example. We are given a circle with center O with 4 points on its circumference, A, B, C, and D, which are joined as shown. At the center of the circle is a given angle COD, which is equal to 100 degrees. We'll start with the angle that we are given, angle COD, which is subtended by the arc CD. We could also draw in a chord CD to make it easier to work with. Angles A and B are both subtended by the same arc or chord CD, and A and B are both points on the circumference. Therefore, angles A and B are each equal to 50 degrees, because the angle subtended by a chord or arc at the center of the circle is double the angle subtended by it at the circumference. Here is a second example, this time with a given angle C of 55 degrees. We need to find the values of the variables x and y. Chord AB subtends angle C at the circumference and the angle labeled y at the center. We know that y must be double the size of angle C, so it is 110 degrees. How do we work out angle x, which is not subtended by a chord or arc? Take a look at triangle OBA. 2 of its sides are formed by radii and are therefore of equal length, making OBA an isosceles triangle. So x is the base angle of an isosceles. Therefore, the angles of triangle OBA are x plus 110 degrees. Using the sum of angles of a triangle, or 180 degrees, we work out that x equals 35 degrees. These are the theorems and converses we've just covered. Equal chords subtend equal angles at the center. The angle subtended by an arc at the center of a circle is double the angle the arc subtends at the circumference. A chord subtends equal angles at the circumference in the same segment. The angle in a semicircle is a right angle.